Hey guys, so in this video we're going to be talking about a very important topic for geotechnical engineers and civil engineers, which is the design of earth retaining walls. So in this lesson I'm going to cover three things. I'm going to give you a quick intro into what are retaining walls, what are they used for. I'm then going to show you some free web software that can be used to help you automate the calculation of these retaining walls, calculating their stability. And then I'm going to break this down in terms of the theory, explaining like how the calculations are done in terms of first principles and all the sort of all the hand calculation methods. So this video is going to be very useful if you're a geotechnical engineer looking for a refresher on how to design retaining walls, and also if you're a student looking for help on your assignment or your coursework. This video will help you to show you some software to help you check your answers and validate your answers. Okay, so without further ado, I'm just going to give you the introduction. So what are retaining walls? So retaining walls is one of the most common methods that geotechnical engineers use to retain earth. So this could be like an unstable slope, or it could be you need to create a sort of level difference in order to get down into sort of like a deeper layer of the earth. So basically you can use retaining walls to give you that resistance or that stability to the soil. And the way this typically works is you would have a concrete object that looks a bit like this, where you basically the way you construct this is you sort of excavate it out and create some sort of temporary propping, and then you can either cast this in, so you could clear all the earth out completely from here and then actually cast this in situ, or it could be precast, and then you could backfill this earth back in. And so typically, that's the method that you use. You kind of like backfill on top of this sort of heel slab, and then you rely on the weight of this earth fill acting on this heel slab to sort of counteract the horizontal force which wants to destabilize this and push it forwards. So you kind of use it. This is also known as a gravity wall because it relies a lot on gravity of this earth fill here to keep the whole thing stable. And then you can install whatever you need over here, like a road or whatever whatever it is you're building. So this is very commonly used, and it's quite an efficient design because it's sort of using the sort of forces of the earth against itself. So it's quite an efficient and like elegant design, you could say. Let's have a look at some software which can help us to automate the design of this. So if you go to www.calcforge.com, I've put the link in the description of this video, and go to the retaining wall calculator. You'll see here a example just very similar to the one we were just looking at, which is this retaining wall. You'll see here on the left, you've basically got a summary of the result. So you'll see here result if it's a pass or a fail, and the utilization. So the utilization at 100% is right on the edge of passing and failing. If it's over 100%, this would fail and it destabilizes and sort of falls forwards or slides. There's different failure methods that I'll explain later. You'll also see here the different geology which can be edited. So all of this can be edited, and you can see here it's made ground. So you have 2 meters of made ground, and then below that is this weathered rock. And on the right is where we can actually control and edit the different parameters that are used in this. So you'll see here excavation depth, base thickness, which is the thickness of this concrete base, the wall thickness, which is the thickness of the wall itself, and then you'll see base length inside, so this will be the length of this side of the wall, and base length outside, which will be the outside of the wall over here. We've not taken any effect of some like backfill on this layer, so we're being like more conservative, let's say, but you can actually get a very small amount of resistance from some layer of backfill on this side as well. But generally it's like quite conservative to just not consider that in the calculation. And then we also can click advanced settings and see we can add a surcharge. So a surcharge up here on this side of the wall. Let's say you've got some like traffic or some sort of load which would be over on this corner. And we can also change the water table as well. So what we can do here is we can actually try customizing some of this. So let's change the wall or the excavation depth to 5 meters rather than 4. So it's increased to 5 meters, and we've seen our utilization has also gone up. So this means that it's closer to failure. So it's still within 100%, but it's closer to the sort of stability limit. So let's change this to now 6, and we see, yeah, okay, 115% utilized, so it's now failing. But we can also change, these different parameters to basically suit our wall. So here we've got a 1 meter inside base length, but let's make this 2 meters, because we've seen, in this example, the heel slab can be a bit more sort of extended than this. So now I've extended this heel slab, and we'll see that we're now back within our utilization limit. So we can go 6 meters deep in this soil and basically still be within our utilization according to this. I can click Edit Geology, and within here I can actually make changes to the ground properties. So you'll see here I've got my 2 meters of made ground, my unit weight, the condition, which is either drained or undrained. So if drained selected, this means that the water pressure has dissipated. So you can use this drained analysis in cases like sand, where the water pressure drains instantly, whereas undrained analysis would be more suitable for clay, which takes longer for the water to drain out. But then you also need to think about if it's short-term analysis or long-term analysis. So short-term analysis for clay, you would consider it being undrained if you think the water wouldn't have left immediately, but drained analysis would be more long-term because it's been loaded for longer and the water's eventually drained out of the clay. So these are kind of important considerations if you're a geotechnical engineer. And then, yeah, you can also add a new layer here. So I can create my own custom layer. So I can make this 2 meters and make this 4, for example, of this. Let's make this 15 of this custom layer, and I can make this 33, let's say. And then basically I can rerun this analysis, and I'll see all of these layers update. And then, yeah, this is causing some problem now, if this was the geology. So you can also edit the geology parameters. And then if I click earth pressure, you're going to see how this is kind of calculated. So you see for each one of these layers of geology, it's calculating this wedge of active earth pressure. So this active earth pressure is acting on the wall at these different points. And then this is assumed that you've got 1/3 from the base, you've got a force acting onto the wall at that position. And also with this one, you need to take account of the sort of how this is a polygon rather than a triangle. And then you need to, our software basically calculates the center of gravity of this force acting. You then also have this small passive pressure, which is, yeah, much smaller, let's say, than these, the combination of all of these combined, but you have a little bit of passive pressure acting on the base of the wall to stop it from overturning. So you then need to resolve all of these forces. And then you need to consider it in terms of bending, sliding, and bearing. So bending is how much the wall is wanting to tip or overturn. Sliding is how much it's trying to slide forwards and backwards. And then bearing is basically your bearing capacity of the soil. And you'll see, interestingly, for this case, it's actually the bearing capacity. So this is Terzaghi analysis. We cover that in our bearing capacity video if you're interested to know how this calculation is done. And if I click full calculation, you'll see a breakdown here of the different Eurocode 7 checks that are being done. So we have the wall overturning check, which is how much it's wanting to overturn and topple, and how these stabilizing and destabilizing forces are calculated. Then you're eventually calculating your stabilizing moment and comparing it to your destabilizing moment to look at the overall stability. Then have wall sliding, so this is how much the walls wanted to slide backwards and forwards. And again, you have your stabilizing forces and your destabilizing forces. You're doing a comparison on these. And finally, wall bearing, which is the Terzaghi analysis I was just mentioning. And here we're calculating our overall bearing pressure, which is average bearing pressure, and then you find your max and your min, and then you're comparing that to your overall bearing resistance to sort of complete this calculation. Now you can also download this entire calculation as a PDF report, so I can click full PDF report to download this. And now let's move on to the theory section. Excavations and retaining walls are used to support earth and create a cavity below the natural ground level. Coming in a wide range of shapes, sizes and materials, retaining walls can include three components: the stem, the toe, the heel slab. Some walls may also include a shear key to resist sliding. Stems can include drainage holes. These reduce water pressure acting directly on the wall. A drain pipe can also be installed and provided along the back of the wall for a similar effect. Coarse aggregate can be added along the back of the wall. This allows water to drain down the drain pipe. The wall surface in contact with the soil is typically treated with some sort of foam or waterproofing. Let's consider two of the most common types of retaining wall. Gravity walls resist earth pressure via the self-weight of the wall alone. Typically these walls are constructed from stone masonry. The second type of wall is the cantilever wall. This is the most common type of retaining wall. These walls are typically used up to a depth of 8 meters below ground level. For this type of wall, the stem, toe and heel act as one-way cantilever slabs. The stem acts as a vertical cantilever under the lateral earth pressure. The heel acts as a horizontal cantilever under the action of net weight of retained earth. The toe acts as a horizontal cantilever under the action of net soil pressure. Here you can see the deformed shape of the wall. Under these combined forces, let's look now at the failure modes of retaining walls. The first failure mode is failure by overturning. This failure mode, the toe will act as the center of rotation and the entire wall will rotate about this point. In the absence of the toe slab, the base directly below the wall stem will act as the center of rotation. The active earth pressure acts as a destabilizing moment on the wall, and the passive earth pressure will act as a stabilizing moment. The weight of soil on the heel slab will act as a stabilizing moment. The second type of failure is by sliding. The active earth pressure applied to the wall acts as a destabilizing force, sliding the wall forwards. The stabilizing force is provided by the friction between the base and the soil below. The frictional force is given by mu times r, where mu is the friction coefficient between the soil and the concrete, and r is the resultant soil pressure. If the active earth pressure is high, and the wall is failing and sliding, then the shear key can be introduced to provide additional sliding resistance. The final type of failure is bearing failure. This is determined by bearing capacity using the Tazagi approach, and more information on this is in our video on bearing capacity. The length L is used to distribute the vertical reaction. Now we will look at how forces are calculated which act on the cantilever retaining wall. First, we assume the ground level is flat and constant. The earth pressure will increase linearly with depth. This means that at the top of the wall, zero earth pressure is applied, and at the bottom of the wall, maximum earth pressure is applied. This earth pressure is known as active earth pressure, or PA. The maximum earth pressure at the bottom of the wall will be Ka times gamma S times H. In this expression, H is the total depth of the excavation. Gamma is the unit weight of soil. Here, Ka is the active earth pressure coefficient based on the Rankine theory and calculated by this expression. Here, the angle phi is the angle of friction or angle of repose of the wall. When the backfill is sloping, the expression changes to this new equation where the additional angle theta is the angle of inclination of the backfill. The pressure PA acts at the centroid of the active earth pressure. This centroid is at a distance h/3 from the base of the retaining wall. The magnitude of this force will be the area of the triangle. The area of the active earth pressure triangle is half times that by the base times by the height. The passive pressure active on the toe side of the retaining wall acts to stabilize the wall. The coefficient of passive pressure Kp is calculated by this expression. This pressure can be excluded from design calculations if so desired to make the calculation more conservative. The final consideration is if any surcharge is provided. This surcharge contributes to active earth pressure. The nature of this surcharge can, for example, result from vehicles or construction equipment. Let's say the surcharge has an intensity of W kilonewtons per meter squared and is uniformly distributed. This pressure will act laterally on the wall with the intensity Ka times W. The force due to surcharge is the area of rectangle, which is Ka times W times height.